think for a second about the sheer amount of digital stuff we do every day. Streaming, searching, endless scrolling.
Mm-hmm.
All that data lives somewhere,
Yeah.
right? In these massive data centers working around the clock.
Right.
What you might not think about is the colossal amount of energy these digital warehouses need just to function, let alone stay cool. How do they even get all that power, and what keeps them from, melting down?
Yeah, that's the crucial intersection we're exploring today. We're taking a deep dive into the vital world of energy management within data centers
Okay.
and the complex networks that power and cool them. We've sifted through several illuminating articles and a really detailed Moxa DCI playbook to bring you, hopefully, a clear understanding of this often invisible infrastructure.
Exactly. For you, our listener, the mission here is pretty simple: to extract the essential knowledge and deliver those aha moments without drowning you in technical jargon.
Right.
And believe me, the scale of this is surprising. Get this. A recent Cushman-Wakefield report projects an astonishing 8.8 times increase in revenue related to AI data centers by 2028.
Wow.
That's a massive jump in just a few years.
And that explosion in AI capability comes with a huge appetite for power. AI servers, especially when they're training those complex models, can guzzle like 5 to 10 times more energy than your standard server.
5 to 10 times.
Yeah. This kind of demand puts immense pressure on our existing power grids. Think of it this way. Deploying just a single AI model training cluster can draw as much power as a small town.
A small town, seriously.
Seriously. It's forcing a radical rethink of energy infrastructure.
So the core to this deep dive is to unpack how data centers are tackling this immense challenge, powering and cooling themselves in this AI-driven era.
Mm-hmm.
We'll be looking at the innovative solutions being rolled out, with a particular focus on the critical role of integrated networks and something called protocol conversion, which might sound a bit technical, but we'll make it crystal clear.
We will.
Okay, so this energy challenge is clearly massive.
It truly is. This exponential surge in data center energy consumption is straining traditional power grids globally. We're seeing increasing concerns about power scarcity in various regions, and data centers are under growing pressure to not only be energy efficient, but also to comply with increasingly strict clean energy mandates.
It's like our digital needs have suddenly outgrown the electrical systems designed way back when. So what's the game plan to keep up?
Well, the big players, companies like Microsoft, Google, Amazon, they're making significant moves to diversify their energy portfolios.
Right.
They're exploring cutting-edge technologies, even things like nuclear energy for a reliable, potentially cleaner baseload power supply.
Nuclear. Wow.
Yeah, and at the same time, they're heavily investing in large-scale renewables like solar and wind farms, often paired with advanced energy storage solutions, to handle the fact that the sun doesn't always shine and the wind doesn't always blow.
So it's not just about plugging into the same old outlets anymore. It sounds like a real transformation.
Absolutely. We're witnessing a shift away from traditional backup power systems, those older N+1 or 2 N+1 models, which are basically just having 1 or 2 extra power units as backups.
Right, the redundancy approach.
Exactly. Towards a more dynamic approach called hybrid energy management. This involves using intelligent technologies like smart grids and microgrids to allocate power resources in real time,
Okay.
optimizing energy use and boosting overall efficiency. The key insight here isn't just mixing power sources, it's about creating an intelligent energy ecosystem within the data center, capable of self-optimization and resilience.
That paints a picture of a much smarter, more adaptable system. Now, you mentioned that integrated networks play a crucial role in all of this energy management. How do they fit in?
Well, a stable and uninterrupted power supply is absolutely fundamental to achieving energy efficiency in data centers. I mean, if the power flickers or goes down unexpectedly,
Yeah,
it can lead to significant energy waste and costly operational disruptions.
makes sense.
And beyond just power, efficient cooling systems are the next big energy consumers in these facilities. They are a key factor in something called power usage effectiveness, or PUE.
PUE, right, I've heard that term. Power usage effectiveness.
Exactly. It's essentially a measure of how efficiently a data center uses energy. Specifically, how much energy is used for the actual computing versus overhead like cooling and lighting.
PUE, got it.
Yeah.
So keeping things cool efficiently is just as vital as getting the power there in the first place.
Precisely. And to handle this intricate balancing act, data center infrastructure management, or DCIM, platforms have become indispensable.
DCIM. Okay.
Think of a DCIM as the central nervous system for the entire data center. It provides a single pane of glass for real-time monitoring of all the critical subsystems.
Everything.
Pretty much. From the operational technology, the physical gear like power and cooling, all the way up to the information technology and the IT staff.
So DCIM provides that crucial bird's eye view. How does optimizing the power system itself contribute to saving energy?
By ensuring that all the power-related equipment operates in the most efficient way possible through smart infrastructure design. This not only leads to significant energy savings over time, but also helps prevent long-term damage to expensive electrical equipment caused by power fluctuations and disturbances. And that directly impacts the data center's overall operational efficiency and longevity.
That makes perfect sense. A stable, well-designed system is inherently more efficient. And DCIM helps achieve this by pulling in data from different management systems, right? You mentioned BMS and...
Exactly. DCIM gains this comprehensive visibility and enables intelligent energy management by integrating data streams from building management systems, or BMS,
like BMS.
which typically control environmental aspects like HVAC heating, ventilation, air conditioning, and electrical power management systems, or EPMS,
EPMS, okay.
which specifically oversee the entire power infrastructure within the facility.
But I can imagine that getting all these different systems to talk to each other and share data, that must be quite a challenge, especially with a mix of older and newer equipment.
You've hit on a major hurdle. A lot of the tried and true operational technology equipment, the power distribution units, the cooling systems, various sensors often rely on older, but still incredibly reliable serial-based communication protocols.
Serial-based, like older tech.
Yeah, think of them as different languages spoken by different generations of machines. A very common one in industrial settings is called Modbus RTU.
Modbus RTU. Okay.
Yeah.
So these established physical systems aren't automatically compatible with the newer, more network-centric IT systems.
Precisely. And that's where industrial protocol converters step in as essential translators.
Translators.
Exactly. These devices bridge the communication gap between these disparate OT protocols like Modbus and another one called BSNet, and the IT-friendly protocols such as Modbus TCP and SNMP. They are the key to achieving that holistic data visibility within the DCIM platform.
Okay, so they make everything speak the same language, basically.
Sort of. Think of the converter as having two different types of outlets and plugs. It takes the signal from one outlet, the old device, and cleverly rewires it to fit the plug of the new system, ensuring the data gets through.
So they act like universal translators for machines. And Moxa, which provided one of our key sources, specializes in developing these kinds of solutions for industrial applications, including data centers.
That's right. Moxa has a strong focus on providing robust and reliable connectivity solutions for large-scale data centers, with a particular emphasis on enabling energy efficiency and the seamless integration of power and cooling systems with DCIM platforms through their range of industrial protocol converters.
Okay, so these protocol converters are clearly vital. But how do they actually do their job? What's going on inside these little boxes?
At their core, industrial protocol converters facilitate communication between incompatible systems by essentially performing a real-time translation of data. This involves not just changing the format of the data, but also adapting the speed at which it's transmitted and completely transforming the underlying communication rules or protocols themselves.
Can you give us a clear, real-world example of this translation in action within a data center?
Sure. Imagine a temperature sensor within the data center that uses the Modbus RTU protocol to communicate it, sends its readings out serially.
Right, the older way.
A protocol converter can take that raw temperature reading, understand it according to the Modbus RTU rules, and then reformat and transmit that exact same temperature value as a Modbus TCP message.
Modbus TCP, that's the newer network one.
Exactly, which is designed to travel over standard Ethernet networks that the central IT system or the DCIM platform can easily understand and utilize.
So it's taking the information from one digital language and rewriting it in another so that different systems can understand each other. What's the internal structure that makes this happen? How does it work inside?
Typically, a protocol converter has an internal component that acts like a master in one protocol. It actively queries and receives data from the external slave devices like our temperature sensor or maybe a power meter.
Okay, it asks for the data.
Right. It collects this data and often stores it temporarily in an internal memory. Then, when an external master device, such as the DCIM system, requests that information using a different protocol,
Mhm.
another internal component of the converter acts like a slave, retrieving the relevant data from its memory and transmitting it out in the format the requesting system understands.
It sounds like a sophisticated intermediary making sure everyone can communicate effectively.
Mhm.
And with the sheer number of devices in modern data centers, hundreds, you said, thousands.
Yeah, it can be thousands.
This ability to ensure interoperability must be incredibly valuable.
Absolutely crucial. Modern, complex data centers.
Yeah.
Yeah, they can have hundreds, even thousands of interconnected devices. DCIM systems rely on this seamless flow of information to provide the automation and that critical end-to-end visibility we discussed earlier.
Right.
Protocol converters are the linchpins in breaking down those data silos that can exist between the often isolated operational technology, the OT, and information technology, the IT domains.
Data silos, that's a great way to describe the problem of isolated systems. So by breaking down these silos, we achieve centralized monitoring, which directly leads to more effective energy management.
Precisely. And it opens the door to other significant benefits, such as predictive maintenance.
Ah, okay. How does that work?
By having a unified stream of data from all the critical equipment, you can leverage analytics, maybe even AI, to identify trends and predict potential equipment failures before they actually occur.
So you can fix things proactively.
Exactly. Minimizing downtime and optimizing resource allocation. It's a huge efficiency gain.
Now, you mentioned that these older field bus protocols like Modbus RTU are still quite prevalent. Why haven't they been entirely replaced by newer technologies? I mean, if there's better stuff out there.
It's a good question. Despite being older communication methods, these protocols are often incredibly robust and reliable. They've been refined over decades of use in tough industrial environments.
Okay, so they're dependable.
Very. Additionally, there's a substantial financial investment tied up in the existing operational infrastructure within data centers. Protocol converters offer a cost-effective way to leverage this dependable legacy equipment without undertaking a complete and very, very expensive overhaul.
Ah, so it saves money, maximizes the ROI, the return on investment.
Exactly. It maximizes the return on investment for data center operators. It's just smarter financially in many cases.
So it's a smart way to bridge the gap between established and cutting-edge technology without having to discard perfectly functional equipment. What about the more modern industrial Ethernet protocols? How do they stack up?
Industrial Ethernet protocols, things like Ethernet IP, they offer significantly higher data transmission speeds and much easier integration with standard IT network infrastructures compared to the older Fieldbus protocols.
So faster and easier to connect.
Generally, yes. However, even with these advancements, protocol converters still play a vital role in facilitating seamless communication with those legacy systems that haven't yet been upgraded to these newer Ethernet-based standards. There's still a lot of that older gear out there.
Right, the mixed environment is common.
Mm.
And what about connecting data centers to the cloud for more advanced data analysis and remote management? Is that where these converters play a role too?
That's where IoT, Industrial Internet of Things focused application layer protocols like OPC UA and MQTT come into the picture.
OPC UA, MQTT. Heard of those?
Yeah, these protocols are specifically designed for efficient and secure data exchange with cloud-based services.
Mm.
Protocol converters can act as crucial intermediaries here as well.
How so?
They translate data from the operational level, from the machines on the floor, into these cloud-friendly protocols. This enables advanced analytics, remote monitoring, even remote control of data center equipment sometimes.
Wow. Okay.
We're also seeing the increasing use of wireless technologies within data centers for applications like mobile robots, maybe remote environmental monitoring. And again, protocol converters are essential for integrating these diverse wireless data streams into the overarching management system.
So they really are like a universal adapter.
Pretty much. A universal adapter for the entire industrial internet ecosystem within the data center.
You mentioned some specific Moxa solutions earlier. Can you give us a couple of concrete examples of how their protocol converters are being used in real-world data center scenarios?
Absolutely. A key product from Moxa is the mGate MB3170. This is a dedicated serial to Ethernet protocol converter,
Yep.
specifically engineered to translate between Modbus RQ-ASCII, those serial protocols we discussed, and Modbus TCP, the prevalent Ethernet-based protocol. This is absolutely critical for integrating those existing legacy devices into modern data center networks.
What are some of the specific features of the MGate MB3170 that make it particularly well suited for the demanding environment of a data center? It sounds like a tough place to operate.
It is. So it's designed for high device connectivity, capable of supporting up to 32 simultaneous TCP server connections and a large number of RTU ASIC slave devices.
So it can handle a lot of connections.
Yeah. It offers flexible network deployment options, including Ethernet cascading and the ability to route data by port or IP address, which simplifies network architecture and management.
Makes it easier to set up.
Crucially, for data center environments, it boasts a robust industrial-grade design. Wide operating temperature range, stringent EMC certifications to minimize electrical interference.
Which must be everywhere in a data center.
Oh yeah, redundant power inputs for high availability, you don't want this thing failing. Comprehensive alarm features for proactive monitoring and advanced troubleshooting tools.
Yeah.
It even incorporates important cybersecurity features and complies with relevant industry standards like IEC 62443.
Okay, that sounds like a really robust and versatile piece of equipment.
Yeah.
Are there any specific real-world examples of how a company has used this in their data center operations?
Yes, there's a case involving a leading computer technology corporation in the United States. They implemented Moxa's Nport serial servers, MGate Modbus gateways like the MB3170, and iLogic remote IOs as a core component of their energy management system.
What was their goal?
They needed a reliable and efficient way to continuously monitor the stability of AC power across their extensive network of data centers. Moxa's solutions provided the necessary connectivity and data acquisition capabilities to link their diverse power devices to their central energy management system.
So Mox essentially provided the communication backbone to get all that vital power data into a single system for comprehensive monitoring. Do you have another example of their technology in action?
Certainly, a major semiconductor manufacturing company in Taiwan utilized Moxa's MGate MB3660 high-density gateways for rapid and reliable Modbus RTU to TCP conversion.
High density, meaning lots of connections again.
Exactly. They had a critical need to monitor their backup power systems with really stringent performance and reliability requirements, particularly in environments with significant electromagnetic interference EMI.
Right, the electrical noise.
Yeah. The MGate MB3660 provided the necessary high port density to connect numerous devices, along with the speed and robustness to ensure consistent data acquisition even in those challenging conditions.
It's truly fascinating how this seemingly invisible layer of technology is so fundamental to the operation and efficiency of these massive digital hubs. So just to recap, protocol converters are essentially facilitating DCIM integration, enabling granular power monitoring, supporting precise environmental control, and even paving the way for proactive predictive maintenance. Can you elaborate just briefly on how they contribute to each of these areas, like the key benefit?
Sure. For DCIM integration, converters are the essential bridges. They allow DCIM platforms to talk to BMS and other OT systems, providing that crucial unified view for optimized cooling and energy management.
Okay, the unified view.
In power monitoring, they enable collection of detailed data from UPS systems, PDUs, generators, smart meters. This allows precise tracking of energy use, identifying waste, ultimately lowering that PUE number.
Better efficiency through data.
Exactly. For environmental control, they integrate data streams from sensors, temperature, humidity, etc., and the cooling systems themselves into central platforms. These platforms then make precise adjustments to maintain optimal conditions while minimizing energy use.
Not cooling.
And finally, in predictive maintenance, by enabling consistent data collection from all sorts of industrial equipment, protocol converters provide the raw info needed for AI and machine learning algorithms. These algorithms can spot subtle anomalies and predict potential failures before they impact operations.
Preventing problems before they happen. Got it. So what does the horizon look like for these vital protocol converters? Where are the key trends pointing?
Well, we're seeing a significant push towards edge computing.
Edge computing, processing data closer to where it's generated.
Exactly. And the increasing integration of AI and machine learning capabilities right at the network edge. This suggests that protocol converters will likely evolve into more intelligent edge gateways.
So more than just translating.
Yeah, capable of not only translating protocols, but also performing local data processing and analysis. This reduces latency and the amount of data that needs to be sent back to the cloud.
Makes sense. What else?
Enhanced cybersecurity will also be absolutely critical. Future converters will need to incorporate advanced security features like zero-trust architectures, secure boot mechanisms, network segmentation capabilities.
Security is definitely a paramount concern. especially with the ever-increasing connectivity of industrial systems. What other developments can we anticipate?
We'll likely see a continued drive towards greater standardization and more open protocol integration. This will foster seamless interoperability across devices from different manufacturers, less vendor lock-in.
Good for the users.
Definitely. And as data centers become more modular and scalable in their design, protocol converters will need to be equally adaptable to these dynamic configurations and increasingly distributed environments.
Flexibility is key.
And finally, with the growing global focus on sustainability and energy efficiency, protocol converters will play an even more crucial role, enabling precise energy monitoring and facilitating the integration of renewable energy sources into data center power grids.
It certainly sounds like they'll only become more critical as data centers continue to evolve and adapt to the demands of the future. So to bring our deep dive to a close, it's clear that the ever-increasing energy demands driven by AI are really fueling a significant transformation in how data centers approach power and cooling.
Absolutely.
And at the very heart of this transformation are these integrated networks and the often overlooked but absolutely essential industrial protocol converters.
Precisely. They function as the vital enablers of efficiency, ensuring reliability, and promoting sustainability within these incredibly complex digital ecosystems.
And now, you, our listener, should have a much clearer understanding of the intricate inner workings of data center infrastructure and the absolutely critical role that this often unseen technology plays in keeping our entire digital world running smoothly and efficiently.
Yeah, which leads us to a final, maybe thought-provoking question. As artificial intelligence continues its rapid growth and drives even greater levels of energy consumption, how will we effectively manage the delicate balance between technological advancement and responsible energy management?
Mm.
And what further groundbreaking innovations in data center infrastructure can we anticipate in the years ahead to help us navigate this critical juncture?
Definitely a lot to consider. We encourage you to delve deeper into these fascinating topics and contemplate the profound implications they hold for the future of both technology and energy consumption. Thanks for taking this deep dive with us.